So we're looking at some of my diamonds. I thought I'd maybe wear gloves and not get hemp seed oil all over everything. And this is just with the north light from the window behind me. I don't have my flash on. Um, and I'm going to turn it on now. And there we go. We've got a little better sparkle here. Diamonds always sparkle around the periphery because the brilliant cut makes the planes of cleavage parallel with this angle here of the pavilion. So they go outwards and catch the light. Diamonds are the only things that do that, except maybe synthetic moissanite and natural silicon carbide if you get gemstone variety. It's hard to find them. It's also hard to find colored diamonds in kimberlite pipes because they don't go deep enough. They are, 5 kilometers deep at the deepest, maybe, maybe a little more, but not much. Fault lines, on the other hand, go all the way down to the semi-molten mantle where the lava for volcanoes comes up, right? And when it cools down as it's moving up to 3,800 degrees, diamonds begin to precipitate out. They're the first thing out of the melt because they have the highest melting point. Below that melting point, they're floating in the molten rock into other things that are coming out. The next thing out is silicon because it's attracted to the carbon. They're both semi-metals with 4 electrons in the outer valence orbit. So it reaches its vapor point, and everything's a vapor at 3,800 degrees except diamond. But the silicon and the diamond are attracted to each other because they're the same, in the same column of the periodic table, the same chemical family called semi-metals. And we use silicon for our computers and stuff because of that property, and we make really cool things out of it, supposedly. And here we are. This is a piece of carbon that formed somewhere between the lowest point, where 3,800 degrees is present, and then it cools. And but in between the silicon and the carbon coming out, the carbon and the silicon coming out, it's just carbon. There's nothing else there. It's all liquid and beyond its vapor point, way, way, way beyond most things' vapor point. Titanium comes out right after silicon carbide, and then aluminum oxide. And I don't think this. I see it in the laboratory over and over and over again. And these are not things, the properties that I made up. You can look them up. And that's how diamonds form. They're formed way, way deep in the earth. The deeper they form, the closer together the planes of cleavage are, because the unit cell of this carbon crystal is squeezed together more, right? Can't help it. It's not magic. It's physics. And the size of that unit cell and the planes of cleavage associated with it determine the color. Also, the deeper it forms, the more carbon-14 is in the crystal lattice. That's why blue diamonds are so special. This is kind of actually lavender. But the secondary colors are blues because it slows the light down and the light red shifts. So and then lighter blue comes out. The colors are not really colors like let's see, tanzanite, for instance, blue, right? Dark blue tanzanite has color all the way across the stone. This is just around the periphery, and then you can see down inside of it to the point of the pavilion as though there was nothing in between. Because diamond is so very, very, very clear because it has double covalent bonds, which makes it the hardest mineral on Earth. Silicon carbide also is 10 on the Mohs scale of hardness. There's nothing else in the 10 category. Nothing. Except AUPT, which also forms down there, 10 kilometers down or whatever it is. And so as it comes up, it gets turned blue and then green and yellow. And I've got some really nice orange ones, but not in this batch. And then red. And the GIA would like you to believe that people irradiate these. Well, you know what, man? I might be able to because I work with radioactive isotopes as a physicist. But nobody else can, man. The Cinta Largo tribe in Brazil, where these come from, couldn't possibly do it because they don't know what it is and they don't know what makes color. And it's not the radiation that makes the color. The radiation makes it sparkle bright because it's giving off electrons from the carbon-14. The color is caused by the closeness of those planes of cleavage, and it gets a little bit more and more wider and wider and wider the higher up it forms, right? The cooler the mix goes, and the less pressure there is. And diamonds hold that pressure. What happens with a kimberlite pipe is it's caused by an asteroid strike. Boom! And underneath of there's a cone of compression. And that cone of compression is on minerals in place, minerals that were already solid when that thing hit. And the ones that have a little bit of carbon in them turn into diamonds because everything else is vaporized. And diamonds precipitate out first as any melt starts to precipitate, starts to cool, right? It's not magic. It's physics. It's just simple physics. And carbon is not rare. Kimberlite pipes are rare, but they don't really produce really big diamonds or really good diamonds. Fault lines, every fault line on Earth produces diamonds. Maybe not gemstones, but diamonds and silicon carbide. And I find them in the Gila River. Fuck. Now we're having fun. In AUPT, this is gold platinum alloy, and the platinum is black in this case, like a black diamond, it's lacking a neutron. And so it's absorbing energy, trying to become one neutron greater and find stability. As platinum, whatever it is, 189 or something. No, 180 something in there. I'd look it up. Unless it's something that I work with all the time, like plutonium. And I know that one, Pu-244. And there's some of that in here too. As well as uranium and other things. Platinum has a radioactive isotope, PT-190, and I find that in here. This red stuff is silicon carbide and diamond. I have green ones, red ones, blue ones, because fault lines extend all the way to the semi-molten mantle, and as they come up, they bring this stuff up. Now, AUPT has covalent bonds. It's a covalent metal rather than a metallic metal, because it forms way deep in the earth and it cools slowly. So there it is. That right there weighs about almost 50 pounds. It's really heavy, 25 kilos, I think. Heavier than 50 pounds. My wife, this was the biggest one she could pick up, so we left the other ones. Nobody's bothering them. They think it's road tar. And it's not. Road tar doesn't weigh 50 pounds, man. This is I don't, 25, 30 centimeters across, and it's square, right? It's a square because gold and platinum form in the cubic system. Actually, face-centered cubic, just like diamond. Face-centered cubic, hexagonal. So you see both symmetries. You'll see cubic this way, hexagonal another way when you rotate it 90 degrees. And I don't know which one this is because it's too heavy for me to rotate at the moment. I'm crippled. But just my legs, my heart, not my mind. And I've been out looking for rocks for 35 years and studying chemistry and physics all my life because my father was a nuclear physicist. So I got a lot of this stuff while I was growing up. And it makes it a lot easier to figure out when you actually know a few things about science. Like black diamonds, this is a black diamond. Black diamonds have carbon-12 in them. The isotope that we find in graphite up on the surface. But carbon always has some of each. Carbon-12, carbon-13, and carbon-14. Carbon-13 is the stable isotope because that's what diamonds are made out of. And diamonds really, really, truly are forever. Unless you get it up to 3,800 degrees, and that's not easy. It's not even easy getting up to 1768 is what platinum and AUPT melt at. But when there's diamond crystals in there, they act like a heat sink. You can take a diamond and hold it in your hand and drill it, polish it without water. They don't get hot. That's one of the for sure ways of knowing you got a diamond, but the colors around the periphery are good enough for identifying pictures of diamonds. And I buy these on eBay. I think I paid $20, less than $20 for this set here from my friends at Longwen in Kowloon, China. China does not have the De Beers Corporation, and they know that diamonds are not rare and not hard to find. This is one I cut a few years ago when I first started playing with them, and you can see the carbon-14 in this makes it glow in any light. This is a north light, late summer afternoon in Phoenix, Arizona, with the light behind me, and it glows in all lights. It can't help it. That light is stimulating the emission of electrons. That's what beta emissions are. They give off electrons as the neutron, the extra neutron in carbon-14, fissions and gives off the mass of an electron at light speed. And that's what makes diamonds glow.